two intersecting planes meet in a straight line. Consider this face of this cube as a plane 1, another face on top as a plane 2. You'll notice that they have a common intersecting lines, which is this line. A line consists of 2 points, point A and point B. We know that a line is determined by at least 2 points. If you remember axiom 3, two distinct planes cannot meet in one point only. Now, but this line lies in both faces of this cube, hence, both faces of this cube have the line in common. 2. A plane is determined by two intersecting lines. Consider this line and this line, they intersect at this point. If we extend these two lines, they also intersect at this point, a point of intersection. In axiom 2, through 3 non-collinear points, one and only one plane can be passed. 3. A plane is determined by two parallel lines. Consider this face of this cube as a plane. A plane has parallel lines, which is this line and these lines. By the definition of parallel lines, two lines in the same plane. If we put another point on this plane, the distance of these lines are equal. Therefore, a plane is consist by two parallel lines. Theorem 3. If a line is perpendicular to each of two lines at each point of intersection, it is perpendicular to the plane of this line. Using this stick, we let this stick lies at any point on this cube. Now, to show that any lines passes through a distinct point on this stick is perpendicular, we let another line intersect at this point. And now, prove that the angles are congruent by CPCTC. This point A and point B, point C is congruent to point A, DC. Therefore, by the definition of a line is perpendicular to the plane if all line passes through its foot is perpendicular. Therefore, the stick is perpendicular to this cube.
Hi guys, it's June and I'll be showing Theorem 4, 5, 6 of solid geometry using this figure. Theorem 4 states that through a point there is one and only one plane perpendicular to a line. You see this line here? If we let this line here intersect at the point of this plane, which is here, and if you remember Colorali 2, you see that at the point of a line, there is more than one perpendicular to the line. So, if you look at here, look at these lines here. If we let this line here be line 1, and this line be line 2 of this plane, and let the stick be another line which intersect at the line. Now, if you remember Theorem 3, if a line, here, a line, is perpendicular to each of two lines, here, here, at the point of intersection, at the point of their intersection, which is here, then it is perpendicular to the plane containing these lines. So therefore, this plane here is perpendicular to this line. Now, we have Theorem 5. Through a point, there is one and only one line perpendicular to a plane. So, if this is our line, and this is our plane. If you remember the definition of line and plane perpendicular to each other, a line is said to be perpendicular to a plane if every line, say here, of this plane is perpendicular to this line passing through its foot. For example, if we let this line here, if we let this stick here be on this plane and this line here containing this plane, they intersect at the foot of this line. Now, imagine that there is a point here of this plane and two lines intersect at that point. There exists another plane here containing this line which intersect at the point of this plane and which is perpendicular to these lines. So therefore, there is only one line perpendicular to the plane. So from Theorem 6, oblique lines from a point to a plane meeting the plane at equal distances from the foot of the perpendicular are equal. And conversely, two equal oblique lines from a point to a plane meet the plane at equal distances from the foot of the perpendicular. Now, for us to show that the theorem is true for all oblique lines, we want to prove that this line here are congruent. Now, from the theorem itself, the points of this line here, this line, and this line here are of equidistant from the foot of the perpendicular line. So therefore, this line here and this line are congruent. For us to show that these lines, oblique lines, are congruent, we want to prove the two triangle form. These two triangles here, you see, two triangles are congruent. Now, we establish that this line here and this line are congruent. If you look at their formed angles, they form a right angles. From the definition of perpendicular and right angles, so they have equal angles of 90 degrees. And if you look at this line here, they have the common side, which is here. So we have a reflexive property. So by SAS postulate, we conclude that these two triangles are congruent by SAS postulate. And therefore, these oblique lines here, by congruent parts of congruent triangle, are congruent. There you have it.
Shit, what's it gonna be? Let's have a let's part of shit. I just try to reach you, so wanna air. Megan Ganta, Missy Wana.